Hello, my name is Ria, and this is my Data for Good AP Stats project, which I did on an analysis of DEI in STEM majors. Okay, so a little bit of background information. DEI stands for Diversity, Equity, and Inclusion. And as probably many of you know, STEM stands for Science, Technology, Engineering, and Math. Recently, DEI has become a priority of many educational institutions and employers as they try to increase the minority group populations within their campus workplace. Racial minorities in STEM fields include Hispanics, which only make up 15% of the workforce, Asians, which are 10%, and Blacks, which are 9%. Women only make up 28% of the STEM workforce, which much lower proportions depending on the STEM field evaluated. So for my project, I wanted to evaluate the proportion of minority populations, which would be, as I mentioned before, females, Blacks, Hispanics, and Asian/Pacific Islanders, or APAs, in various STEM majors. Why it matters. DEI in the workforce increases cultural awareness, critical thinking, and it encourages people to consider things from a new perspective. STEM fields specifically are historically lacking in diversity, and this underrepresentation of certain populations can lead to bias in both products and services that are provided by these fields. So I began my project with data collection on my subject. I used numerical data on proportions of minority populations in STEM majors that I isolated from data that I obtained from the National Center for Education Statistics, which is a branch of the U.S. Department of Education. The majors for which I selected data were biological and biomedical sciences, engineering, health profession and related programs, mathematics and statistics, and physical sciences and science technologies. To do my actual analysis, however, I narrowed it down to one major, engineering. My raw data was obtained from the population of all U.S. graduates for each corresponding major from 2010 to 2021. I then displayed my data in a table, which I created to reflect both the years and the major, and then the exact number of baccalaureate graduates in each minority group. As I said before, once I had gathered this data, I limited my analysis to just the major of engineering for each of these groups. I also included a control group so that I could evaluate how the overall numbers were changing over time over the past 11 years that I evaluated data for. Okay, then I created a data display which was a graph to show how the actual numbers grew over time, from 2010 to 2021. I graphed each of the data for each minority population, and as you can see here, it forms a relatively straight line. Okay, from there, I formulated my research questions. Number one, I said, can the data of minority proportions in engineering majors be approximated by a linear regression model? So that was my first test that I did. And my second one was, can an appropriate model be used to predict the minority proportions in engineering majors for bachelor's degree graduates in 2023? Okay, so for each of my minority groups, I created a graph, and then I used a linear regression model to create a line of best fit that could fit the data. For my first minority group, which is females, I created a line of best fit that was y equals to 1,831 x minus 33,670,495. For this line seems to fit the data pretty well, and that is confirmed by its R value of 0.9916, which indicates that there is a strong positive linear correlation between year and proportion of female engineering majors, and the R squared value of 0.9832, which means that 98.32% of the variation in proportion of women in engineering majors can be explained by its approximately linear relationship with year. Once I received this data, I graphed it with a residual plot, which also showed no clear patterns or outliers, or curves that would indicate that a linear model was not appropriate. I completed a similar model for each of my other minority groups. For the Black minority group, I also found an exceedingly high R value and an R squared value, indicating that a linear model was once again appropriate. The residual plot also shows no clear patterns or outliers, which confirms this hypothesis. I continued to do this for each of the minority groups. For Hispanics, which also had a R squared value that indicated a strong positive linear correlation, and an R value that indicated that, and an R squared value that explains 98.89% of the variation in proportion of Hispanic people in engineering majors by its approximately linear relationship with year. So basically, there's one more, which is the minority group of Asian and Pacific Islanders. This also had a very high R value and an R squared value. So overall, for all four of the minority groups, we found that it could be adequately represented by a linear model, indicating that as more years passed, the proportions of these minority groups in STEM fields did grow over time, specifically engineering. Okay, so the next statistical question that I wanted to answer was whether or not I could use the linear regression model that I created to predict a value or a proportion for each of these groups for 2023. Okay, so first I used the model that I created to create a prediction for 2021, for which I had actually been able to collect data for. Okay, so first for the female group, I got a value of 31,756, which is greater than the actual value of 30,555. And then I used that same model to predict the 2023 value of 35,419. So I did this same test for each of these, finishing it with the Hispanics, Black, and Asian Pacific Islander minority groups. For each of these, the value that I predicted was greater than the actual number, which I believe could be possibly attributed to the COVID-19 pandemic, which resulted in fewer bachelor's degree graduates overall. So I do think that would explain this difference. And I still think that it would be useful in predicting the 2023 values as we're coming out of the end of the pandemic. So the 2023 values we predicted also seem to show a nice growth in the proportions of these minority populations, which is definitely exciting because it shows that DEI efforts are working and that we can hope that they will continue to work as they should to help support this growth in the future. To conclude, because the linear model is appropriate and can be used to make pretty accurate predictions of these proportions and statistics in the future, we can conclude that there is a positive pattern of association between year and proportion of minority groups for engineering majors, which is also supported by our graph. So therefore, over time, since 2010, as DEI initiatives have become more popular and have been prioritized by educational institutions and by hiring, it's just been a bigger part of the admittance processes. We can see that STEM majors and therefore the STEM workforce are becoming more diverse. This data supports the idea that companies, organizations, and educational institutions should continue to place an emphasis on improving DEI. So my reflection, what went well? I learned a lot about the importance of DEI, and I really enjoyed seeing how actual data that I was able to collect and graph. I could see the actual growth in minority populations, and I've seen how DEI has directly impacted these minority groups. And their proportions in STEM majors. Some of the challenges that I had was that I had originally planned on doing a chi-square test, but I couldn't find sample data, so I had to change my research questions and project goals accordingly. I also had to input most of my data by hand, which was time-consuming and tedious, and I actually didn't end up using most of it because I decided to limit my tests to just engineering majors. For further study options, I was thinking that maybe someone could collect data over more years to see the long-term changes to DEI. We could also try to expand our research to include worldwide statistics, which would be possibly comparing the proportions of minority in STEM majors between countries. Okay, this is my works cited. Thank you for listening.